Welcome. This is Year 8, Competence-Based Middle Years Program Level 3, Sciences. This is workshop number 1. In this workshop, we're going to go back to basics. This is, we are going to see the basic concepts in kinematics. We're going to train ourselves in converting units, and we will analyze the uniform rectilinear motion, URM. So let's start with the basic concepts. The most basic of them all is the position. The position is the point occupied by the moving body in space. It's represented by r, from the Latin radius, or distance to origin. The trajectory is the line followed by the moving body, the succession of points it occupies in space. We call speed, and represent it with v from the Latin velocitas, is the rate of change of that position, whether it changes position faster or it changes position more slowly. We could say in general terms, and we will have to make some precisions later, that it is the distance covered divided by the time it takes to cover it. And therefore it's usually measured in meters divided by seconds, meters per second. The average speed, or Vm, the m coming from the Latin media, is used when that rate of change of position does change along time, and bodies move in different ways along a different period of time. We define for rectilinear motions that the distance covered is the difference between the positions, and that is only when we do not have a change in the sense of the movement. Because if we have a change in the sense of the movement, the distance covered is the entire succession of positions, but the difference between the initial and the final point may be even 0. So in rectilinear movements, when there is no change in the sense, we can say that the average speed is the distance divided by time. So it's the final position minus the initial position divided by the time it takes to go from one point to the other. So it's delta r divided by delta t. Remember that the Greek capital delta means variation, final value minus initial value. So the average speed is the final position minus the initial position divided by the time we have when we reach the final position minus the time we had when we were at the initial position. Variation of position divided by variation of time. We just said that the rate at which a body moves can change along time, and it can go more slowly at the beginning and faster at the end, or the other way around, or it can vary more or less randomly. We call acceleration, and we represent by an A, the rate of change of the speed. We could also say it is the variation of speed divided by time, and it is measured, given that it is variation of speed, meters per second, divided by time, second, it is measured in meters divided by second squared. The average acceleration for an entire period of a movement is the speed change divided by the time it takes to perform that speed change. So it would be the final speed minus the initial speed divided by the time at the end of that variation minus the time we had at the beginning of that variation. Therefore, delta V, variation of speed, divided by delta T, the variation of time. In the System Internacional, or international system, which was defined in the 18th century France, the basic quantities for kinematics are the length and time, and we will also use mass because we are going into dynamics afterwards. The name of the base unit for length is the meter, and it is represented by a lowercase m. The base unit for mass is the kilogram, and it is represented by a lowercase k and lowercase g, not uppercase k, lowercase k, lowercase g. And the basic unit for time, it is the second, lowercase s, not seg, as you will see wrongly sometimes. It is only s. Let's now see an example of converting units. And we will do the conversion of 0.1 kilometers into a decimeter. We know that a kilometer is many times a meter, 1,000 times a meter, and the decimeter is smaller than a meter, is 0.1 meters. So there will be several decimeters in 0.1 kilometers. Let's find how we do that. We do that through conversion factors. Conversion factors are always equal to 1, and we use them to convert the units. We multiply them, that is why we call them factors, and we use them to convert units, that is why we call them conversion factors. The value of a conversion factor, as said, is always 1. Let's see how we find them out. We know that a kilometer is 1,000 meters, therefore 10 to the third power meters. We want to convert kilometers into decimeters. We want to get rid of the kilometers. So we're going to divide that equality by 1 kilometer, the left-hand term. And we obtain as follows: 1 kilometer divided by 1 kilometer equals 10 to the third meters divided by 1 kilometer. That is 1. Again, now with the decimeters, we want to insert the decimeters in our expression. So we go to the definition of a decimeter. A decimeter is 0.1 meters or 10 to the minus 1 meters. Again, we want to insert the decimeters, so we divide by the right-hand side term. 1 decimeter divided by 10 to minus 1 meters equals 10 to minus 1 meters divided by 10 to 1 minus 1 meters, and that is 1 as well. Now we go back to the original amount we had, 0.1 kilometers. And we are going to multiply that 0.1 kilometers by the conversion factors needed to convert the units. First of all, we multiply it times the conversion factor to remove the unit we want to get rid of, which is 10 to the third meters divided by 1 kilometer, which equals 1. So we are multiplying times 1. We're not changing anything. And then we need to insert the unit we are looking for. We use the other conversion factor we have, also equaling 1. So when we multiply times 1, we don't change anything. And we put that conversion factor after the first one. So now we have that long expression, but we have kilometers at the top and kilometers at the denominator. We have meters at the numerator, we have meters at the denominator, so we can cross them over. And we remain only with decimeters in the numerator. We rearrange that series of fractions, and we have the 0.1 times 10 to the third power divided by 10 to minus 1 decimeters. Rearranging that, again, we obtain that it is 0.1 times 10 to the fourth, which is 10 to the third decimeters. So 0.1 kilometers equals 10 to the third 1,000 decimeters. Let's now see an example of uniform rectilinear motion, URM. Our example is going to be an ant moving along a ruler. We assume that the ant is moving uniformly along that ruler. At time 3 seconds, it passes position 10 centimeters on the ruler, goes on walking, and at time 8 seconds, it passes position 20 centimeters. And we are asked to calculate the speed in meters per second and also the equation of the movement. So let's go step by step. Speed. Speed, as we know, is the distance covered divided by the time it takes to cover it. Let's analyze what the problem tells us. The problem is telling us that at time 3 seconds, so that is t0, it is at position 10 centimeters. So that is position 0. And then at time 8 seconds, which is time 1, it passes position 20 centimeters, which is position 1. Now we can calculate the speed because we do have the final position R1 and the initial position R0, and we know the time at which we reach the final position, which is T1, and we know the time at which the ant was at the initial position, which is T0. We can calculate the difference between the positions and the difference between the times. That is 20 minus 10 centimeters, and it's 8 minus 3 seconds. So it is 10 centimeters in 5 seconds, which is obviously 2 centimeters per second. But remember, we were asked to give that speed in meters per second. So we need to get rid of the centimeters and we need to insert the meters. Now, we know that a meter is 100 centimeters. So if we multiply times a meter divided by 100 centimeters, we are multiplying times 1. It is a conversion factor. And now we can cross over the centimeters and we have 2 meters divided by 100 seconds, which is 0.02 meters, 0.02 meters per second. We have the speed. Let's now see the equation of the movement of the ant. We assume it is uniform rectilinear motion, and we know that the equation for the uniform rectilinear motion, the position is given by the expression position at any time equals initial position plus speed that multiplies the value of time minus the value of the initial time. But we know all that, so the position at any moment equals the initial position, which is 10, as we just saw, plus 2, which is the speed, times the time at any instant, minus 3, which is the initial value of time we were given. We solve the parentheses, and we have 10 plus twice the time plus twice minus 3 in brackets because it is a negative number. We multiply that, and it is 10 minus 6 plus twice the time, which is 4 plus twice the time, centimeters, with time in seconds. And that is all for today. As always, enjoy science and life in general. Thank you very much.